Hello. In this topic, we are going to look at an overview of the law of conservation of momentum. Now, early on at the beginning of the unit, we framed out this idea about motion, that we can be descriptive in terms of kinematics of the motion, and that we are looking at dynamics, the things that causes objects to move and change their motion. And we said that there are two fundamental concepts that explain why objects change what they do, and those are momentum and energy. And so what guides momentum is the law of conservation of momentum, and the law of conservation of energy guides energy. Within momentum, we said that there are some important concepts: inertia, impulse, rate of change in momentum, which is the definition of force, and that's why force is a related concept to momentum. Force isn't really fundamental in terms of the operation of the universe. It's a concept that has been created to help us understand momentum, but it's not fundamental in the way that momentum and energy are. And so we see forces related to energy. We just want to situate that construct there for us in terms of where conservation of momentum is. So, if we are to define the law of conservation of momentum, what we would say is the total momentum of a system remains constant unless acted on by a force external to the system. So some key parts to this here. The total momentum of the system remains constant. Okay, so the total remains constant. A force external to the system. And so basically what that means is if there is a force external to the system, the force is providing an impulse which changes the momentum of the system. But what we can see then that the system itself, if there's a change in momentum, it's about a force and an impulse external to it. The main rule I want you to take away from the law of conservation of linear momentum is that the rule is the law. And that rule is it is always true. There are no exceptions. As my hero Dwight Schrute once said, that is the law according to the rules. Well, this is the law according to the rule. It is always true. It is the law of conservation of linear momentum. In every situation, you can count on it. So it allows us to predict and describe the motion accurately because this is always true. So let's start out with a simple formula to describe this. Well, the formula we would use is to say, well, the initial momentum is equal to the instantaneous momentum. In other words, the initial momentum is equal to the momentum at any instant in time. So therefore, it's equal. No matter what event happens, the momentum will be equal to each other. Now, this causes us to look at this a little more deeply when we apply it to any particular situation. Is we need to take into account all the particles. That means the momentum of all the particles. So let's say that in the beginning there is one particle, and it splits into three particles. Well, that means the initial momentum, which was the momentum of the first particle, is equal to the new particles, the momentum of each of those particles. So the momentum before, where there was one particle, is equal to the momentum afterward. That one particle split into three particles. And so we can generalize this more and say, however many of particles there are initially, and that ... means going onward, we could add any number of particles, is going to be equal to the momentum of all those particles, whatever number there are afterward. Now, this prime designation means afterward. and we say that as p prime. So it's the momentum afterward, some of the momentum afterward. And the number of particles doesn't need to agree, but this must constitute all the particles in the system, and this must constitute all the particles in the system. So we might imagine three particles moving along together as our system, and one of them explodes into three other particles, which would leave five particles on the other side. So in accounting for the momentum, we need to consider all the particles of the system before and afterward. So we could also rewrite this formula as saying the sum of the initial momentum is equal to the sum of the momentum afterward. And so we can also see that this prime in this case becomes a little bit redundant because we are using the convention of the plane variable, meaning instantaneous. And of course, that's a distinction to the initial momentum. So those are the main pieces here. This is, if we were to choose one, we could say this is the law of conservation of momentum, or this is the law of conservation of momentum. They are the same thing. I find this second one that I'm highlighting again in blue is a little bit broader, and so we may use that. You'll see me use the first one very often or interchangeably as we proceed through the topic. Now let me just draw a parallel here to energy. The law of conservation of energy. The law of conservation of energy, not surprising, says the total energy of a system remains constant unless acted on by an outside force or by a force external to the system. So we can see from the previous page where we have momentum and energy, we said that the force is kind of a supporting concept or related concept to momentum and energy. Force can bring about changes in the momentum of a system, and forces can bring about changes in energy to a system. And so that's the relationship thereof. But there's no such thing as the law of conservation of forces. There's nothing like that. And that's why momentum and energy are more fundamental concepts. So the law of conservation of energy is always true, except when you put a qualifier on that, except when on a scale inside an atom. Now we think of nuclear scale. And at that point, our dear friend Einstein, around the turn of the end of the 19th century, beginning of the 20th century, came up with this world's most famous equation. Energy, changes in energy bring about changes in mass. So this is basically a corollary that says is that the total energy and mass of the system remains constant. Now, this is not a topic that is covered in AP Physics, and this is not a situation we will run into in AP Physics or need to deal with. But I want you to be aware that there is an exception to this, and that's at these extremely small scales where mass and energy are interconverted with each other. And so therein lies the exception, but that just means we modify the definition to the total energy and mass of the system. And so when we look at the universe on a grand scale, the total energy and mass together, all accounted for, remains constant over time. So at the Big Bang, we had the universe which was completely energy being converted to mass. And there are all kinds of processes going on throughout the universe where mass and energy are converting back and forth to each other, but that is beyond the scope of this course. And so in our course, the law of conservation of energy, it is always true. Now notice it's conservation of energy, and there are many different types of energy. There are what we call mechanical energy. which is what we focus on in AP Physics. Those are things like kinetic energy. Oops, kinetic energy. Already thinking ahead to what I'm going to write next. The kinetic energy. There's the potential energy that things have because of gravity, EPG. There is the potential energy that things have because of a spring. And those are the three types that we will consider in this course. Now, there are other kinds of energy: thermal energy and wave energy and sound energy and chemical energy. All of these are types of energy. But we speak of mechanical energy, we're speaking of a subset of all the different types of energy. All right. But when we are talking about conservation of energy, that is all of the types of energy. So let us first diagram out the different types of situations we are running into. So whenever we have particles or bodies interacting, we can ask ourselves, which type of interaction is it? So we have our interactions. And the first of these we would call an explosion. I call an explosion. And if you put your hands together and you act that out, well, if you act out an explosion, things are moving apart from each other. The other types of interactions we have are collisions. And collisions come in two types. There are bouncy collisions, and there are sticky collisions. Bouncy collisions are like billiard balls, pool balls colliding. And sticky are when objects combine. So you might imagine like a dartboard covered in felt, and you have some balls that have Velcro on them, and you throw those balls at that dartboard, they would stick. And so that is where we have two particles become one. It also may occur when there is deformation of one or more of the particles. And kinetic energy is converted to thermal energy. Now, examples of that you've already seen. We've watched several videos of tennis balls, of rubber balls, of golf balls. And those balls, they compressed. Well, when they compressed, the molecules, the atoms, the polymers inside those move and flex. And that moving and flexing is equivalent to friction. And so that then generates heat. So some of that kinetic energy does work on the ball, and the object will actually increase in temperature. And that increase in temperature will be equal to the loss in kinetic energy. So there's two ways to think about these sticky type collisions. Bouncy type collisions have a special name. They are called elastic, which means the kinetic energy remains the same before and after. The other ones are called inelastic, and the kinetic energy decreases in an inelastic collision. And they decrease as a percent. And we could take that, the final kinetic energy, and divide it by the EK0. So if the kinetic energy afterward and initial are equal, we get a number of 1. If all of the kinetic energy is lost, then we have a number of 0. So the elasticity can be expressed as 100% or 0% or any combination in between. So what I call this, when we say things are elastic or inelastic, it's a false dichotomy. Dichotomy meaning two categories. Yes, you could say something is completely elastic or completely inelastic. But what do you call it when it's 50-50? Well, we say it's inelastic And it turns out in the universe, elastic, pure, true elastic collisions don't happen because whatever the particles are, will collide with each other. They'll create internal vibrations. There will be some movement of the matter inside, and therefore a tiny amount, an infinitesimal amount of energy may be lost. So when we speak of an elastic collision, it's an ideal. It's an ideal case, elastic. Okay? So false dichotomy, it can range anywhere from 100% to 0%. But in any case, every time we lose a noticeable amount, we call it an inelastic collision. So in some ways, I want to make one more connection here. In some ways, explosions, when we compare them, are more like a sticky collision than a bouncy collision. See, an explosion is not an example of an inelastic collision because it's not a collision, but it shares this trait that the kinetic energy initial is not equal to the kinetic energy afterward, which is what happens in a sticky collision. The initial kinetic energy is not equal to the kinetic energy afterward. But in an elastic collisions, the kinetic energy initial is equal to the final kinetic energy. In a collision, the kinetic energy decreases. And an explosion, the kinetic energy increases. Now, if you were to say or ask, say, wait a minute, what about the law of conservation of energy? Well, what we have in this case is we have zero kinetic energy becoming some number of kinetic energy afterward. Let's say it's 10. Well, looks like we created energy. We didn't. It's just that the chemical kinetic energy in the explosion plus the kinetic energy will equal the kinetic energy afterward. So 10 plus 0 equals 10 in that particular case. So interactions, when you see particles or matter interacting and changing their motion, you want to ask yourself, is it an explosion or is it a collision? If it's an explosion, we know certain things are going to happen. The kinetic energy will be more afterward than it was before. The collisions in this case can be broken into two categories, sticky and bouncy. In the sticky, the kinetic energy decreases. In the bouncy, it remains the same, but that is an ideal situation. So let's take a look at the formulas for an explosion. Oh, we're actually going to pause there. We're going to break this into another section, which is 5.5. We're going to look at explosions in a greater depth.